Hello and welcome to EE323 Lecture 15. Today I'll do a few Opamp examples. You can find this in your book, sections 2.2 and 2.3. So let's start out with example 1. What we see is an Opamp configuration here where we have resistor R1, resistor R2. We have an output voltage, we have an input voltage of 0.5 volts. We have two currents coming in, I1 and I2, and an output current and a load current. So the first question we'd like to answer here, we'd like to find VI, I1, I2, VO, IL, IO, AV, AI, and AP. And we're going to assume this is an ideal op-amp. So the first question is, what is this op-amp configuration? And the answer to that is that this is an inverting amplifier, right? And we can tell this is inverting because the input is going into the negative terminal of the op-amp. And then the next question, number 2, is what is the equation for the output voltage for this configuration? So this is an inverting amplifier, so we can write that V out is equal to minus R2 over R1 times V in. And so this would equal minus 20 k ohms over 1 k ohm times 0.5 volts, which is going to equal minus 10 volts. In other words, the voltage gain AV is equal to minus 20 volts per volt. So with that, we've been able to figure out what the output voltage is and what the voltage gain is. Okay, moving on here. Moving on to questions 3 and 4. Is there anything we know about this circuit by inspection? So what we're trying to solve for here is V1, I1, and I2. V1 is this interior node here. So by inspection, because we're in negative feedback, positive terminal is being held at ground. And we're in negative feedback, this holds the negative terminal equal to the positive terminal. So V1 is equal to 0 volts. And we also know by inspection that I1 is equal to I2. That is, all the current flowing in I1 flows into R1 and then into I2. Because the input resistance to our op-amp is infinite, no current flows into the op-amp, so all the current I1 has to flow into I2. So if we were to solve for the equation for I1 now, we know the voltage across I1, and from Ohm's law we can find the current, so we can write that I1 is equal to 0.5 volts minus 0 over 1 k ohm, which would equal 0.5 milliamps. We know that also is equal to I2. Okay, moving on to the next part of this problem. Here we're going to be solving for IL and IO. Find the equation for IL. So IL is the current through our load, and we can solve for IL because we know the output voltage and we can apply Ohm's law. So we can write that IL is just the voltage across the resistor, which would be minus 10 minus 0 divided by 1 k ohm. So that's going to be equal to minus 10 milliamps. This minus 10, this is V out, right? And so that's IL. We can also solve now for IO by doing KCL at that output node. We can write that the current coming in is the current going out, so that I2 plus IO is equal to IL as it's drawn. In other words, IO is equal to IL minus I2. So IO is equal to minus 10 milliamps minus 0.5 milliamps, which is equal to minus 10.5 milliamps. Keep in mind what this means for I/O. It's a negative current, is that the current is actually flowing into the op-amp. This was just an application of KCL. All right, so the last few questions that we have here. On example 1, we need to solve for the voltage gain, current gain, and the power gain. The voltage gain we already know from an earlier slide. That's the voltage gain was minus 20 volts per volt. And the current gain, AI, that's going to be equal to the load current, IL, divided by the input current, II, which would be minus 10 milliamps, divided by 0.5 milliamps, which is equal to minus 20 amps per amp. Now we can solve for the power gain. We can say the power gain is equal to the voltage gain times the current gain, which would be minus 20 volts per volt times minus 20 amps per amp, which would equal 400 watts per watt. Okay, moving on to example 2. Okay, we have an op-amp configuration here, which we can consider a trans resistance amplifier. And then the question here is find the input resistance, the trans resistance Rm, and the output resistance Ro. So we have a 10 k ohm resistor in feedback, and again the current I1, the input current is flowing all through the 10k resistor because no current is flowing into the op-amp itself. So by definition, the trans resistance Rm is equal to the output voltage divided by the input current when the current at the output is equal to 0. So this is definition of Rm. And so we can say that Rm then is equal to, well, hold on, we can say that V out is equal to minus I1R. And so V out divided by, I in R. So V out divided by I in is equal to minus R. And then that's equal to Rm. So Rm is just equal to minus 10 k ohms. All right, now we need to find the input resistance and the output resistance. Well, the input resistance is going to be equal to the input voltage divided by the input current. So that would be Vn minus Vi divided by the input current. But you'll notice that this is a short here. There's no resistor there at all. Therefore, this is equal to 0. So the input resistance is 0. And by inspection, looking at the output resistance seen looking at output, Ro, the output resistance of our op-amp itself is 0. Therefore, the Ro of our circuit is equal to 0 as well. All right, and so now we can change example 2 a little bit. Now that we've figured out the trans resistance and the input resistance and the output resistance of that amplifier, we can apply a source to it. So if we apply a source that has a current of 0.5 milliamps and has a source resistance of 10 k ohms, what would the output voltage be? And so what we can write now is, again, all this current, this 0.5 milliamps, it's going to get to this node here, and all of it is going to be going into IN because the input resistance is 0. And then all that current is going to flow through the 10K. Therefore, we can write that V out is equal to the voltage at VI minus the voltage drop across the 10K. That will give us V out. So that would be 0, which is VI, minus II times R. Right? So V out would be equal to minus 0.5 milliamps times 10 k ohms. So V out would be equal to minus 5 volts. All right, moving on here to example number 3. Okay, so we have a circuit here that has 2 inputs. It has V1 and V2, and the question is figure out what the output voltage is. First question we'd like to answer is, what kind of configuration is this? Notice that these 2 inputs are going into the positive terminal, so this is a non-inverting amplifier. And then the next question is, what kind of a circuit analysis should we use? Well, anytime we have a linear circuit and we have 2 inputs like this, we could use superposition to help us solve the problem. All right, so let's apply superposition. So to apply superposition, what we're going to do is turn off one of the inputs. And this we'll start off first by turning off V2 and assuming our only input is V1. And when we turn off V2, the voltage source becomes ground. So V1, now what we'd like to do is find V plus as a function of V1. And you can see that the 2K and the 3K set up a voltage divider. So we can write that V plus from 1, coming from 1, input 1, is equal to V1 times the voltage divider, which would be 3K over 3K plus 2K. And so that's going to be equal to 0.6 V1. Now that we have V1, we can treat this like a non-inverting amplifier and figure, V plus 1, we can treat this like a non-inverting amplifier and figure out the output from voltage V1. So we can write that V output 1 is equal to the non-inverting amplifier, which is 1 plus R2 over R1 times 0.6 V1. And so that comes out to be 1 plus 9K over 1K times 0.6 V1, which comes out to be 6 V1. So V out 1 is equal to 6 V1. Okay, so then what we'd like to do is turn off V1, that is ground V1, and use V2 as our input. And in that case, the positive V plus with the input of V2, we call it V plus 2, is equal to V2. And now we have a resistive divider going the other way. So that's 2K over 2K plus 3K, which is equal to 0.4 V2. Now the output V out from input 2, V out 2, is equal to 1 plus 9K over 1K times 0.4 V2, which is equal to 4 V2. Now, to find the final output voltage, we can apply superposition now, and we can write that V out is equal to V out 1 plus V out 2. So in other words, V out is equal to 6 V1 plus 4 V2. All right, moving on here to example 4. So we're given a small voltage to amplify. In this case, we have a voltage of 5 millivolts. I want to deliver this to a load with a voltage of greater than 5 millivolts, a 1 kilo ohm load with a voltage of greater than 5 millivolts. We also have a source resistance of 50 ohms. So we have two op amps we can choose from, an inverting amplifier and a non-inverting amplifier. The input resistance needs to be at least 1 mega ohm, and the output resistance should be near 0. We have a range of resistors between 1K and 100K ohms. So first question that we need to answer, what gain do we actually need from our inverting or non-inverting amplifier? So we can write that the magnitude of the gain is equal to the magnitude of the output voltage divided by the magnitude of the input voltage, which would be 5 volts over 5 millivolts. So we need a gain of 1,000, right? So the magnitude of our gain must be greater than or equal to 1,000. That's the first question we can answer here. Now, we need to figure out which amplifier we're going to use in this case. So if we need a gain of 1,000, right? We need a gain of 1,000. Question is, can an inverting op amp by itself do that? So the max gain of the inverting amplifier, we're using the inverting op amp. Max gain is equal to minus R2 over R1, which would be equal to minus 100K over 1K, which would be minus 100. In other words, the magnitude of the gain is 100. So that doesn't meet the spec of 1,000. What about the non-inverting op amp? Let's try that. The max gain in this case is equal to 1 plus R2 over R1, which would be 1 plus 100K over 1K, which would be 101. So the absolute value of the gain would be 101, magnitude of the gain. So that doesn't work either, right? And so the question then becomes, what is the solution? If we can't solve this with either op amp, what are we going to do instead? And the answer would be that we can cascade amplifiers, right? So if we're going to cascade amplifiers, so the answer, we're going to do some cascaded amplifiers. So if we're going to cascade these amplifiers, which amplifier should be the input stage and why? The input stage should be the non-inverting amp. And why? Because the input resistance of the non-inverting amp is very close to infinite, really large, and that satisfies the input resistance spec. Now, which amp should be the output stage and why? Well, both amps, the output resistance tends to 0, so really either amp would work. So if we cascade a non-inverting with an inverting here, well, we can figure out the total gain. First thing we would do is find the gain of the first stage. So the gain of the first stage here, that is the gain to V1. We could write that V1 is equal to 1 plus R2 over R1 times Vs. In other words, V1 is equal to 1 plus 9K plus 9K over 1K times Vs. So V1 is equal to 10 Vs. And for the second amplifier, R4 and R3, we can use different values. So we can write that for the second amplifier, that's the second stage here. We can write that V out is equal to minus R2 over R1 times V1. In other words, V out is equal to, in this case, we'll choose minus 100K over 1K times V1. In other words, V out is equal to minus 100 V1. And so if we combine these two using smaller resistors than we could have, we can write that V out over Vs is equal to V1 over Vs times V out over V1, which would be minus 100 times 10, which is minus 1,000. Or in other words, the magnitude of the gain is greater than or equal to 1,000. And we didn't even have to use the largest amplifiers. We chose the largest resistors. We chose a 9K for R2 here instead of the largest possible resistor to make this a little cheaper if we're actually going to fabricate something like it. Okay, that is the end of this lecture. Thank you very much.